All right, welcome to this explainer. Today, we're diving into a genuinely massive engineering challenge. I want you to think about the most advanced machinery in the world right now. We're talking autonomous drones fighting through high winds, chemical reactors processing super volatile elements, or even just inverted pendulums trying to constantly balance themselves. These are highly complex, totally unpredictable systems. Honestly, it's essentially the engineering equivalent of trying to balance a broom on your nose while riding a unicycle in the middle of a hurricane. And if we don't control them perfectly, they can rapidly and disastrously spiral out of control. So today we're exploring the absolutely brilliant evolving science of how we keep these chaotic machines perfectly in check.
And that brings us right to the core question of our whole journey today. How do you control a system when you don't even know all its rules? In engineering, we call this nonlinear dynamics, and man, it is literally like trying to tame a wild animal on the fly. The environment is constantly changing, random external disturbances are hitting the system out of nowhere, and the underlying mathematical rules that actually govern the machine's behavior, well, they're either completely unknown or they're constantly shifting over time. We have to somehow tame this beast in real time.
Okay, let's dive into this. Here is our roadmap for today. First, taming nonlinear system chaos. Then, sliding mode control basics. After that, AI and online identification, followed by adaptive neural and fuzzy SMC. And finally, optimizing controllers with ISA.
Starting off with Part 1, Taming Nonlinear Chaos.
Before we contain the beast, we really have to properly understand the chaos we're dealing with. Look, in a textbook, a machine behaves predictably, but out in the real world, systems like an inverted pendulum on a moving cart or a continuous stirred tank reactor, they don't follow perfectly predictable linear rules. If a sudden gust of wind smacks a drone or a random temperature spike hits a reactor, that's an unknown external disturbance. Standard linear math equations simply fail here because they rely on the principle of superposition, which, just completely goes out the window when things get chaotic. And when these control systems fail, we're talking millions of dollars lost, or worse, catastrophic industrial accidents.
Moving right along to Part 2, Sliding Mode Control Basics.
So, how did engineers actually solve this chaos initially? Well, they built a mathematical cage. It's a fundamental, kind of brute force method called sliding mode control, or SMC for short. At the absolute heart of SMC is something called the sliding surface. In plain English, you can just think of the sliding surface as this invisible, highly strict path that we define mathematically. We take the chaotic thrashing system and we aggressively force it to follow this exact path. Once the system's trajectory hits this surface, the controller essentially does whatever it takes to keep it sliding right along that boundary. And here is the actual math behind that boundary. Now, what this equation does is nothing short of mathematical magic. It takes a terrifying, higher-order tracking nightmare where you're trying to calculate multiple chaotic variables all at once, and it just magically transforms it into a simple, first-order stabilization problem. Essentially, as long as you can drive this value s down to 0, your system behaves exactly the way you want it to. To actually make this happen, SMC relies on two completely distinct control laws working together. First up, you have equivalent control. You can think of this as the smooth guide. It calculates what the system should naturally do to stay on the path, assuming we have perfect knowledge of the model. But, spoiler alert, we never have perfect knowledge, so we need the switching control. This is the aggressive enforcer. If the system gets bumped off the path by a random disturbance, this discontinuous force violently pushes it back into line.
But, and it's a big but, standard sliding mode control has a fatal flaw. Its kryptonite is something called chattering. Because that switching control acts instantly and so aggressively, it creates this intense vibration. Imagine a driver just violently jerking a steering wheel left and right over and over just to stay perfectly on a painted line. That rapid, high-frequency switching excites unmodeled dynamics in the machine. In the physical world, this severe vibration can, literally, shake the physical hardware apart, just completely destroying motors and actuators over time. Which brings us to Part 3, AI and online identification. We desperately needed a way to keep the robust, unshakable strength of SMC, but entirely eliminate that destructive chattering. So we had to evolve. Instead of just reacting with brute force, what if we taught the system to think, learn, and predict for itself? This is where online neural network system identification comes in, and online just means it's learning in real time. This incredibly complex AI process basically boils down to 3 highly digestible steps. Step 1, the system measures its current physical output. Step 2, it calculates the prediction error, so the difference between what the AI thought would happen and what actually happened. And Step 3,
It updates its own internal network weights using an optimization algorithm called stochastic gradient descent. Think of it as the AI rapidly taking microscopic steps down a hill to find the absolute lowest possible point of error, instantly getting smarter for the next millisecond.
Now, what's really interesting about this visual is that we are quite literally watching a machine learn to understand a chaotic system in real time. Notice how the neural network's output layer weights, or W2, evolve over a 20-second window as the AI observes an inverted pendulum. Over on the left, at time 0, the weights are all tightly packed. It's basically just guessing. But very quickly, through that continuous loop of stochastic gradient descent we just talked about, the weights expand, they adapt, and they lock into this stable oscillating rhythm that perfectly matches the nonlinear dynamics of the pendulum.
And just how effective is this real-time learning in practice? Well, when tracking the pendulum's angle, the network achieved a root mean square error of just 0.0506 radians. That is an absurdly low error rate. It proves just how terrifyingly accurate the artificial neural network becomes at predicting the physical chaos. And it does the whole shebang entirely without human intervention.
Now for Part 4, Adaptive Neural and Fuzzy SMC.
This is where we merge the aggressive, brute force controller with our new, highly adaptable AI brain to finally solve that nasty chattering problem. As we compare standard SMC with adaptive fuzzy SMC here, the evolutionary leap is super obvious. Standard SMC relies on fixed boundaries. You actually have to know the maximum possible disturbance beforehand, and as we know, it causes severe chattering. But indirect adaptive fuzzy SMC, it acts like a mathematical shock absorber. It uses fuzzy logic, which is basically human-like if this, then that reasoning, to dynamically approximate those unknown system functions. It completely smooths out the control signal, basically eliminating the chattering problem, while still forcing the system to safely ride that sliding surface. So the crucial point is right here in the tracking. Notice how the solid line, the actual physical output of the system, virtually mirrors the desired dotted trajectory. The fuzzy logic has successfully tamed those harsh switching mechanics. It rejects random external disturbances without vibrating the hardware to pieces. It's smooth, it's incredibly elegant, and it is highly, highly robust.
And finally, Part 5, Optimizing Controllers with ASA.
Okay, but there is one final piece of the puzzle here. These adaptive and neural controllers are incredibly complex. They have multiple parameters and gains that need to be tuned absolutely perfectly to actually work. So, how do we find those perfect settings automatically? Enter optimization algorithms for controller design, specifically the Adolescent Identity Search Algorithm, or AIS. And yeah, it's named that because much like a teenager rapidly trying out different personalities until one finally fits, this algorithm autonomously searches thousands of parameter combinations in fractions of a second to find the absolute perfect settings. It is an incredibly fast, meta-heuristic optimization method that eliminates human guesswork entirely.
And this brilliantly illustrates the result. When ASA activates, its optimization cost, which is basically its error rate, drops like a total rock to near zero in just a few dozen batches. It rapidly zeroes in on the optimal parameters. And the direct physical result of that? A mass spring damper system achieving absolutely perfect balance almost instantly, driven by those exact optimized parameters. The algorithm found the mathematical sweet spot that a human engineer might literally spend weeks trying to locate.
So, let's take a step back. From the brute force mathematical cages of standard sliding mode control, to the adaptive real-time learning of neural networks, to the lightning-fast parameter tuning of optimization algorithms, we have completely transformed how we interact with chaotic systems. Through the fusion of AI and control theory, we are moving from simply programming machines to literally teaching them how to survive in a wildly unpredictable world. If our algorithms can learn to tame physical chaos in fractions of a second, what other unpredictable forces in our world are just waiting to be mastered?